Hello, welcome to the Recitation Week 8 for EE2423 Network Theory. So let's review what we learned last time. So last time we did some problems involving inductor and capacitor, and the voltage across inductor is equal to L, which is inductance in Henry multiplied by the rate of change of the current. Since the current across inductor cannot change instantaneously, so the voltage across inductor uh, will appear when the current is changing. If the current is steady state, or the rate of change of the current is zero, then there's no voltage across the inductor. Okay, so that's why the voltage across inductor is given as L times di over dt. The same with capacitor, but in capacitor is the voltage that cannot change instantaneously, and the current flowing through the capacitor is given as C, which is capacitance, and the unit of capacitance is farad. So the current is given as C times dV over dt, and that's the basic things about inductor and capacitor that you need to know to solve this kind of problems, right? So as usual, if you have questions, please come to my office hour, or you can send me email, and I'll be glad to help you to solve your problems. Okay, so on this occasion I will solve one problem very similar to what we did last time. So here is the circuit. I only have one problem for you today. So you have voltage source 24 volt, resistor 2 ohms, switch, inductor is 200 millihenry, and current I flowing to that direction. So that's the definition of the direction of our current flowing through this inductor. And we have switch, right? So the first switch is here. At t less than 0, the switch is located at point B, but when t is greater than or equal to 0, the switch is moved to point A. Okay, and here we have another resistor 10 ohms, and this time we have current source instead of voltage source, and it gives 8 amps. Okay, so the question is, okay, let's put it IL, this is VS, this is IS, this is R1, R2, this is L. Sorry, so let's put this on different colors, say green, so VS, IS, this is R2, R1, L. Okay, so the question is, what is ILT? So the expression of the current flowing through this inductor for t greater than or equal to 0. So what is IL of t when we have the switch located at point A, essentially, right? So that's the question here, and no initial condition is given, so we have to figure out ourselves what are the initial conditions for this problem. Okay, so let's find the answer. So first, when t is less than 0, what do we have? Said when t is less than 0, then we have this circuit right here, right? We have this circuit for a quite long time. So in that case, then the inductor will behave like just a wire or a cable, right? Because it has settles for quite some time. So what we have is 24 volt, this is Vs, 2 ohms, R1, sorry. So this is what we have, right? And this is IL. Okay, this is 40 less than 0. This is what we have. So what is IL here? IL is simple. It's a voltage 24 divided by the resistor 2, which is 12 amps. Okay, so we can use this as initial condition for the inductor. So we can say for t greater than or equal to 0, at this time the switch has moved from point B to point A. So we have, let's draw instead of copying it. So this is what we have. Okay, this is L, R2, IS. This is 8 amps. This is 10 ohms, 200 millihenry. And we still have the IL, which is something that we need to find. Sorry, this is R2, and that's it. So this is when t is greater than or equal to 0 and the switch is at point A. So this is what we have. Based on previous calculation, we know that IL is 12 amps. So we know that IL0, or the initial condition for the circuit, is 12 amps, right? So you can think that this inductor has already charged for quite some time, right? It has stored some energy inside it, and the energy is represented by this initial current 12 amps. All right, and given the setup, we want to find what is IL there. Okay, all right, so what do we know? We know that, let us define, okay, plus minus here is VL, or the voltage across the inductor, and let us also define VR as the voltage across this R2 resistor. And as such, we can apply the node voltage, right? So what do we know with node voltage? We know that the current there is IS, right? Is IS. This current here is VR over 10, and this current here is IL, right? So using node voltage, we have IL, right, plus the current flowing through this resistor, which is VR over R2, right, plus IS equals 0. So that's the first equation, guys. Do we know any other equation? Well, let's see. So VL here, VR here, and since this inductor and resistor they are in parallel, right? So we know that VL must be equal to VR. Okay, so I can substitute VR with VL. VL R2 plus IS equals 0. Okay, but what is VL? We know that VL is the voltage, right, across this inductor, and VL, actually VL of t is L dIL of t over dt, right? Because this is the formula for inductor, so we can substitute that VL into this equation right here. IL plus L over R2 dIL over dt, right, plus S must be equal to 0. Okay, so let's put this on the other side. So I have IL plus IS equals minus L for R2 and dIL over dt and I can do this as well. So I have minus R2 over L dt equals dIL over IL plus IS, and then let's integrate from 0 to t minus R2 over L d tau, right, and integral of this from IL0 to IL of t, right, 1 over x plus is dx, and what do you get? You get e to the power minus R2 over L. Sorry, you don't have t, right? For now you only have minus R2 over L t minus 0, just 0. Okay, how about this? Is natural logarithm log of x plus absolute value of x plus is from IL0 to IL of t, but this is actually natural logarithm of IL t plus is over, sorry, IL0 plus is, and then here where you apply the exponential, so minus, sorry, e to the power minus h over lt equals this thing over here, right? Okay, so you know that IL of t is minus is plus IL0 plus is e to the minus R2 over L t. But what is R2 over L? R2 is 10, L is 200 millihenry, which is 0.2 Henry. 10 over 0.2 is 100 over 2 is 50. And IS is what? IS is 8, IL0 is 12. Okay, so you can substitute those values. IS is 8 plus 12 plus 8 e to the power minus 52. You will get, let's just use this. Minus 8 plus 12 plus 8, 20, e to the power minus 50t, and this amps, right? Don't forget the unit amps, and this holds for t greater than or equal to 0. Okay, so this is the solution for this problem, and yes, IL of t for t greater than or equal to 0 is given by this equation here. Alright, and if you're wondering whether your solution is correct or not, then you can do sanity check. Okay, what I mean by sanity check is you can check, since this equation holds for t greater than or equal to 0, then if t is 0, then you should get back your 12 amps, right? Because that's the initial current of the inductor when t is equal to 0. Okay, when t is 0, if you set to 0 there, you have e to the power of 0, which is 1. Okay, 1. So minus 8 plus 20 is 12. Okay, so you will get back your 12. And what happened when t is going to infinity? Well, you can see here. Okay, so this circuit will be going on for quite some time when t is greater than or equal to 0, right? So what will happen when t is approaching infinity? Then again, this inductor will be like a wire, so you have a short circuit there, right? When t is approaching infinity, then this will be behaving like a wire, so you have a short circuit there. And since it is a short circuit, theoretically or ideally there's no resistance there, but you still have 10 ohms resistor here. So since this wire doesn't have any resistance, then all the currents from this currents will be flowing through this wire instead of this resistance, right? So because why would the electrons flowing through something that has resistance in it? So essentially you will have minus 8 amps when t is approaching infinity. So when t is infinity, then this will e to the power minus infinity, or 1 over e to the power infinity is 0. So you will have minus 8 amps. So that makes sense. So that's how you do a sanity check for your solutions. And since we have confirmed, then we can now be sure that this equation is correct. Okay, so I hope what I explained today makes sense. And still, if you have any more questions, do not hesitate to contact me, send me emails, come to my office hour. I will be more than happy to help you. Okay, thank you.